Okay, let's start. I hope I'm audible to everyone. Yes, no? Okay, great. Okay, so welcome to the third lecture of algorithm design and analysis. So today we are actually formally going to delve into the world of algorithms, although of course we have done some warm up over the first two lectures. We talked about an algorithm for multiplying two long matrices, multiplying two long numbers. And we, had a peek a bit into how to analyze recurrences because those are important to analyze, especially the paradigm of algorithms, which we are going to start off with, right? Which we call the divide and conquer paradigm. Now, what exactly is divide and conquer algorithms? So the idea is what it says basically. Okay, so you are given a problem which has a certain size, but well, you don't really know how to handle this entire problem all at once. So what you do is you try to break up that problem into smaller and smaller chunks. Okay, and now you try to solve those smaller sub problems, right? But now again we may ask that, okay, you started off with a certain problem, you broke it into smaller parts, but we don't know an algorithm to solve the smaller problem. So here is where the power of recursion steps in. And what we realized when we went through the multiplication algorithms, we saw a couple of them, that all we need to do is just keep on recursing until we reach a point where we can just solve, where the problem is so small that we can essentially solve it using what we call brute force. Okay, so brute force means different things in the context of different problems, but typically it will mean that the problem becomes so small that the solution is almost trivial in that case. Exactly, it's primitive operations. Okay, now so that's divide and conquer. Now of course divide and conquer is not only about dividing and conquering, but it also has a third component which we call the combining part. Yeah, because remember, up to step 2 all we did was we conquered the sub problems, but ultimately we need a solution to the bigger problem that we started with, right? So that's where the combine part steps in. So basically we take the solutions to the smaller sub problems and we combine all of them in order to get a solution to the larger problem. Okay, so this is like the overall paradigm. Yeah, of course we are going to see several examples of how this paradigm is put to use, but it's good to keep this in mind. Okay, and one important aspect which I might readily tell you, that we are going to study a sort of a similar paradigm at a later point in the course, which we call dynamic programming, which also has a very similar flavor. Although it's not exactly doing the same thing, but it has a similar flavor of breaking up a problem into smaller sub problems and trying to solve them, and then again breaking up and so on. But there are some qualitative differences between these two paradigms. And one important difference, if I may say, is that in case of a divide and conquer algorithm, we always attempt to divide the problem into a constant fraction. So if I have a input of size n, then I will make sure that the sub problems that I divide it into is each piece is at least sufficiently large. Each piece is something like, let's say, okay, it's best if you can divide it into two equal parts, but sometimes it might not be possible depending on the problem you are solving. But at least it should be something like, let's say, 1/3 and 2/3, or even 1/10 and 9/10. It should not be something like 1 and n-1. Yeah, that's not typically what we do in divide and conquer. I'm not saying that it's not possible. You can still write such an algorithm, solve the recurrence and get some running time, but typically we don't call that a divide and conquer algorithm. Okay, so enough of high level talks. So let's get into business now. Okay, so what is the problem that we are looking at today? So suppose you are given an array, and just to make life simple, I'm assuming that the array contains distinct natural numbers. So it's an n size array. It contains the natural numbers from 1 to 3 all the way up to n. Okay, and it's in any arbitrary order. Remember, the array is not sorted or anything like that. They're just given in arbitrary order. Now, what is the quantity that we are interested in? We want to count the number of inversions in the array. Okay. Now, what is an inversion? Well, this is the formal definition. So here is the formal definition of an inversion. So I'm looking at the array and I'm trying to identify a pair of indices I and j such that I comes before j, but the number which is stored at the location I is actually bigger than the number that is stored in the location j. As simple as that. So any such pair I call an inversion in my array. Okay? So just to make sure everybody understands what an inversion is, what is the maximum number of inversions that can happen in an array? How many inversions can be present? Okay, okay, good. Right. So it's not n over 2, but it's n choose 2. Okay, that's why I wanted to make sure that everyone understands the difference between that, the definition of inversion. So inversion means I'm counting every pair which can potentially swap their spaces, right? Okay, now I'm not saying that it can be exactly n choose 2 or something like that. But the order would be roughly like n square. So it can be as large as, theta of n square or order of n square is all I'm saying. Because there is a possibility of every pair being inverted in your array, right? So anyway, so let's look at an example. So suppose you are given this array. So what are the inversion pairs in this array? Let's see. So is the number 1 inverted with anybody? Clearly not, because 1 is the smallest element in this array and it appears in its correct position essentially. So it's the first element in this array. So clearly 1 is not taking part in any inversion in this array. Okay. Let's look at 3. Is 3 involved in any inversion? It is, right? Right? Because 3 and 2, they are inverted. So that counts for 1 inversion. Okay. 3 does not take part in any other inversion, I guess. Okay. Is 5 taking part in any inversion? It is, right? So 5 is actually taking part in 2 inversions. Why? Because 5 is part of this inversion. This is clearly an inversion, but 5 is also part of this inversion. Okay. So so those are the 2 inversions. Okay, 2 is taking part in only 1 inversion, but that we have already counted for. Yeah, we have already accounted for the inversion 3, 2 or 2, 3, if you want to look at it like that. 4 भी एक inversion में part ले रहा है, which is 5, 4, which we have already counted, right? And 6 is not again taking part in any inversion. Okay, so the total number of inversions in this case is 3. Yeah, सबको clear हो गया what I mean by inversions in an array? Is the problem clear? So all we want to do now is design an algorithm that will count the number of inversions in an array. Okay, great. Okay, so I guess many of us have already started to believe that, okay, this problem has a very easy naive algorithm which runs in something like theta of n square, or let me not say theta, something like order of n square. Okay, why? Well, all you can do is you can fix one index of the array and you can just compare it with all the indices, all the other indices of the array which are occurring after that. Yeah, and you can check whether this guy takes part in any inversion or not. Now clearly there are n elements, so you need to just run 2 loops, one outer loop and another inner loop in your code, and it will give you the right answer. Okay, so n square is like it's a trivial algorithm. Okay, any questions so far? Right? Okay, but clearly we are not satisfied with n square. What we really want to see or really want to design today is an n log n algorithm. So you want to design an algorithm to count inversion that runs in order n log n time. Okay, good. Now, okay. Now here is the point that right. So so remember we already so there is a subtle point here. Okay, so let me actually ask you this question. Can we actually output all the inversions in order n log n time? Okay, so why not? So the claim is that if I ask you to output all the inversions, then I cannot achieve this in order n squared time. Well, why is that? Clearly, what we realized is in the worst case, the total number of inversions could be as large as order n square, yeah, or theta of n square. But if that is the case, then even outputting will take order n squared time. Then how are you even supposed to design an algorithm which runs in n log n? So ये जो n log n की बात हम कर रहे हैं, that is only to count the number of inversions, not to output. Okay, if you are required to output the number of inversions, then there is really no other way but to resort to an order n square algorithm. Okay, all these cleverness that we are going to talk about, they just doesn't really matter anymore. Great. Okay, so now before I actually delve into the algorithm, let me give you a small motivation, or at least uh, some sort of idea of why this might be actually useful. Why are we even why are we even bothered about counting inversions? So one interesting application is the following. So suppose there are two customers on an e-commerce website, and they have been asked to rate the products, okay, for some reason. So they are asked to rate a bunch of products. So you can imagine that, so both of them rates the products, okay, and this will give rise to two different arrays. Now you can count the inversions, number of inversions between these two arrays. That will tell you that in how many cases these two people have rated some product in the reverse order. Okay, and this we can use as some sort of a similarity measure between the two customers. Okay, and this sort of similarity measure, they are often used in order to recommend products. So suppose now person one is going to buy something and person two has already bought some similar items, then depending on this similarity indices, Amazon or Flipkart might recommend you certain things. Okay, so I'm not saying that this is the only algorithm to do recommendation, but it's an important component. It's called collaborative filtering. It's an important component of many modern recommender systems. Okay, so just to put this problem in context, there is also a sort of a geometric interpretation of this problem, which you are going to see in your programming homework. Okay, I'm not going to tell you about that, but yeah, let it be a surprise. All right, so how are we going to design an algorithm for? So we will do step by step. Okay, so I understand that many of you are familiar with this thing. That's okay. I mean, for them, it will be a repetition, but I really want to, because this is the first algorithm we are going to do formally, I'm going to go slow, and I'm going to actually sort of arrive at the algorithm, right? Rather than directly telling you what the algorithm is. Okay, so here is the idea. Remember, we are trying to do a divide and conquer algorithm. So suppose A is divided into two parts, X and Y. And as I said, I'm not specifically mentioning here like what is the size of X and what is the size of Y. But since it's a divide and conquer algorithm, we should always attempt to divide it as uniformly as possible. Okay, so you can assume that each is of size n half. Okay, so yeah, I mean, there is no hard and fast rule. You can also divide it as n third and 2n third. That's perfectly fine. But for the purpose of, not for the purpose of lecture, I mean, the natural way is to divide them into two equal parts. Okay, so now once we have these two parts, so the first n half elements form my x and the next n half elements form my y. So now I am going to give names to the inversion pairs that occur in the original array A according to this division. I'm just going to give them some labels. Okay. So the first category, I call them the left inversions. Okay. So when do I call an inversion a left inversion? Well, if I can visualize it in the form of this array. So suppose the first half is called X, the second half is called Y. Now, if there is an inversion in A such that both the indices I and J are in X, then I call this a left inversion. Remember, all these names that I am giving, they are in the context of this particular division that I am making. If you do a different division, then the left inversion will change. Okay. Suppose instead of dividing in the middle, if you divide a bit towards the left, then of course the number will change accordingly. Okay. But I guess all of you understand what left inversion means. Okay. Similarly, I will also define right inversions. So what is right inversion? Well, if both the indices appear in Y, then I call it the right inversion. Okay. And then there could be a third category of inversion. Yeah, I think which is already many of you have guessed what the third category of inversion is. So it's those inversions such that, so suppose again, this is my array. So that's my X and that's my Y. So the third category of inversions are those for which I belongs to the left side and J belongs to the right hand side. Okay. And I call them the split inversions. Okay. So on the basis of this division X and Y, I'm able to categorize my inversions into three different classes. Yeah. Left inversion, right inversion, and split inversions. Right. And we will see how these become useful when we design the algorithm. Okay. Any questions so far? So again, just to make sure that everyone understands, what are the left inversions in this picture? Or let's say, what is one example of a left inversion? Yeah, 5-3 is a left inversion, right? So actually, instead of writing 5-3, let me write it as x2 and x3. Okay, so I'm writing it in terms of the indices of the array. And okay, by the way, our disclaimer is, in most of the lectures, I will assume that arrays start at the index 1. I hate this idea that arrays start at 0, because then I have to write n-1. I don't like that. I want to get rid of that complexity. And I always assume throughout this lecture that my arrays start at 1, unless there are some special instances where the 0 is particularly necessary. Okay. So with that convention, yeah, x2 and x3 is an example of a left inversion. Okay, so I think you can figure out what the right inversions are. Are there any split inversions? Right. So y3 and y2 is a y3 and right. So okay, but in terms of indices, what is a split inversion? Which are the split inversions? Okay, so for example, yeah, x2 and y2 is an example of a split inversion. Okay, and there are others. So yeah, so I think we all understand now what these inversions are, and I'm sure you'll be able to figure out the rest. Yeah, there are not many more. I guess there are only 3 inversions in all. So yeah, right. Right. Yeah. Janvi, just patience. Yeah, we are going there. Yeah, we'll go there. Okay. Now said that, so now let's put this entire thing into the framework of divide and conquer algorithms. Yeah. So why are we saying that? Okay, does this fit our paradigm? So division is more or less clear. So I want to divide my array into 2 equal halves, let's say X and Y. Okay. Now, basically, if I'm able to compute these 3 kinds of inversions, then I'm done. Why? Because there are no other kinds of inversions. There could only be these 3 kinds of inversions in my given array. Okay. How will I compute the first 2 categories? How do I compute the first 2 categories of inversion? Exactly. That's where the recursion comes into picture. Because remember, if I look at the left inversions, then there is nothing special going on here. Okay, it's exactly the original problem. The only difference being that now I am only focusing on one half of the array. Yeah, so it's a sub array that starts at 1 and ends at n half. Similarly, for y, it's a sub array that starts at n half plus 1 and ends at n. Okay, so both these I can solve, quote unquote, using recursion. Okay, so solve via recursion. Okay, right? So now what is the key challenge now? What is the only challenge that we are left with? Well, the only challenge that we are left with is to count the number of split inversions. Okay, that's the only thing that we need to take care of, right? Because then we have a complete algorithm. So what kind of running time should we aim for when we plan to, okay, how do we compute the split inversions? Remember, from the recursive calls, what we get back is the number of left inversion and the right inversion. And now we have to compute the number of split inversions and just add them up, right? So what kind of running time should we shoot for the third category if we want an n log n algorithm overall? Right. Okay. So we need an order n time algorithm in order to be able to compute the split inversions. Okay. So design order n time algorithm. Okay. Yes. How? That's a good question. I mean, we are coming to that, right? Okay. So Manas, are you asking like how do we implement in order in time, or how implementing this in order in time gives us n log n? Which one is your question? So if it's the second question, then we will come to that. But if it's the first question, then I guess you just need to apply why we need n. Okay, that's a, okay. Let's get back. Why we need n. Okay, so suppose I'm able to count the number of split inversions in order n time. Okay, then what is going to be the overall running time of my algorithm? Well, I can then just write a recursion. Why? So the recursion would be, so the runtime would be 2 times, so Tn equals 2 times Tn half. Why? Because I'm calling a recursion on 2 arrays of size n half. And then if you are able to implement the counting of split inversions in the entire array across x and y in linear time, then all you need to do is add an order n here. Okay. And now if you apply master theorem or any other method of your choice, you will realize that this will actually give you Tn equals to n log n. Okay, so that is why we are shooting for an n log n algorithm. That is our combined part. Okay, good. So here is the high level idea. I think this is just like what I just said. This is just kind of, okay, so this is what I call pseudocode. I am not sure if many of you have seen such things in the DSA course. So okay, so let me also tell you, so when you submit your homeworks or you write your exams, everything is acceptable. You can write a C code or a Python code or a Java code, but honestly, what I love the most are these pseudocodes, right? So when you write a theory question, try to stick to pseudocodes. It's a combination of English and real syntax. If it confuses you, doesn't matter. You can just write everything in your familiar syntax. But typically in the lectures, I would use such things. Okay, I would not be very precise about the exact language that we are going to use, but rather I'm going to write the algorithm more in a high level way. Okay, so now this is the high level idea of the algorithm, right? So okay, of course we need to take care of a base case. So if n is really 1, then I don't really have to do anything. I just return 0, because if there is one element in my array, there is no way that that could result in an inversion. So I just return 0. Okay, and now I do the usual thing. I split it into 2 halves. I call the recursions, and finally I call this subroutine, which I call count split inverse. And this is what we are going to, see how to implement that in order n time. Okay, now as many of you have, I was looking at the chat, many of you have realized that basically we can reuse an idea which we have already learned, which is merge sort. Right. So this algorithm, this problem seems to have relationship with sorting, because after all, remember, what is an inversion? Well, an inversion is something which the sort subroutine needs to correct. Yeah. So inversion is kind of a wrong thing as far as a sorted array is concerned. So all sorting is doing is basically correcting these inversion pairs. So now we can start to get an idea that, okay, instead of correcting, all we now need to do is just count the number of inversions. So maybe we can reuse most of the ideas that we know. Okay, right, Kevin. So it's essentially a measure of how far we are sorted from. Yeah, you can use this as a measure, and that's why I talked about the similarity measure thing. So you can compare two arrays, and the number of inversions in one compared to the other will tell you how similar or dissimilar these two arrays are. It's some measure of dissimilarity. Okay. Now the point is that okay, so if x and y are unsorted, okay, so if x, y are unsorted, so I'll take the question, Shubho. If x and y are unsorted, then it's tricky. Okay. So suppose I have this subarray x, which is not sorted, because remember, so far we have not yet talked about sorting or anything. I mean, we are just counting inversion. So if x and y are unsorted, then this seems very tricky to do. How on earth are you going to even count the number of split inversions in order n time? Because remember, the number of split inversions can still be of order n square. Okay. So if you think about it, this is actually a non-trivial problem that we are trying to solve. We know that the number of split inversions can be as bad as, let's say, n square over 4 or something in the worst case, but we are trying to count this in linear time. So this is not at all something trivial that you are doing, right? And it's not at all obvious that why this should work at all. And clearly, if the two arrays are unsorted, then this cannot be done. Yeah, then this is tricky to do. I don't know how to do it. But what we will realize uh, a bit more formally in a minute, that if the arrays are sorted, then we have an advantage. Then we actually have some hope that we will be able to compute the number of split inversions in linear time. So let me quickly check what Shubha was saying. We could also use insertion sort and binary search to do the same. Shubho, but insertion sort itself takes n square, no? So I don't know what you have in mind though. Maybe, yeah, because insertion sort is not really divide and conquer. Yeah, so the problem, okay, so let me take a minute here. So the problem with insertion sort is, I know why you are saying binary search, because indeed in insertion sort, you can find the correct position to insert an element. That is fine. But then you need to be able to shift the other elements one place to the right in order to insert this element in its proper place. So that actually takes away a lot of time. So I don't think insertion sort is a good way, but your intuition is absolutely correct. We need to use ideas from sorting. Right. So, okay. So, yeah, so I'm not talking about in place or anything. Yeah, that's again, that's an implementational thing. So there are several ways to do this. Yeah, if you're really bothered about space. So no, I'm not. So Gaurav, I'm not claiming this is an in place algo. This will not be an in place algo. Yeah. So this will have a similar idea exactly as we, okay, let's see. I think I'm jumping guns a little bit, but let's see how to solve this problem. So what we realized is, okay, or not realized, I mean, what we are hoping that if the two subarrays x and y are sorted, तो ये जो recursive call से हमारा दो आ रहा है x and y, Of course, the recursions give me the number small x and small y, which are the number of left inversion and the right inversion. But suppose it also gives me back a sorted version of this arrays x and y. Okay, so all I'm saying is that you should ask more from your recursive calls. So your recursive call should not only count the number of inversions in x and y, but it should do some additional work and also give you the sorted versions of x and y. Okay, you ask your recursion to do that. And of course, if it's not only about asking, you also have to do that, because you have to send it to one level upwards. Yeah, unless you are the Raja, you are the node, you're the root node. Okay, of course, if you are the Raja, then you don't need to do anything. But if you are, any level down, then you will also need to do this. Okay, so let's now actually formally establish the connection between merging and counting split inversions. Okay, why are we saying since the last 5 minutes that merge sort or something like that can actually help here? So let's quickly recap what is the merge subroutine. Yeah, so let me actually take this. I think this is the best rather than going to the pseudocode. So here is what we do in merge. So this figure is a bit bad. So suppose the first half is x and the second half is y. Okay. And remember, now I am asking for a sorted subarray. I am asking from my recursive calls to return me the sorted subarrays x and y. So these are individually sorted. Okay. Now, how does merge work? Well, I initialize 2 pointers at the beginning of the subarray x and at the beginning of the subarray y. So one pointer is the first pointer I call I, and the next pointer I call j. And now I just have to use a third array where I'm going to dump the sorted version of the combined array. So I will combine x and y and I dump the sorted version. Remember, I'm just talking about merge sort now. I'm just talking about the merge operation. And we will see how counting split inversions can just be sneaked into this thing. Okay, so what do we do? Well, basically we run a third counter, let's say k, from 1 to n, and at each point I check the elements that the pointer I is pointing to and the pointer j is pointing to. Okay, so for example, in the first iteration, when k equals to 1, both are pointing to the elements, the respective the respective first elements of the two subarrays. Yeah, and which one do we choose? Well, we choose the smaller of the two. Yeah, so currently I is pointing at 1, so I just dump 1 here. Okay, what happens next? Well, I advance I. Yeah, I don't advance j yet, because why not? Because j is pointing towards the element 2, but that has not yet been placed in this array. The final array d. Yeah, the output array. Okay, I again do the same thing. I compare x of I and y of j, and now I see that y of j is actually smaller than x of I. So as far as the merge subroutine is concerned, it will ask me to dump 2 in the output array. Okay, but now we make an observation. I claim that this actually exposes a lot of split inversions. Which are the split inversions that this exposes? So whenever I am placing an element from the second subarray to the final output array in my merge procedure, there are some split inversions that are exposed. So which are the split inversions? Well, in this case, it is exposing the split inversions 3-2 and 5-2, both of them, right? So I write 2 here, but I can also now keep sort of a counting, keep track of this count, right? So all I'm saying is whenever in your merge procedure, you are taking an element from the second subarray, then it exposes a number of split inversions. In this case, it exposes 2 split inversions. So let me just write 2 here because it has exposed 2 split inversions. And let's continue. So now j has advanced, but now again, I is the smaller element, so I just dump 3 here and I don't do anything. Yeah, I don't need to increase count because now I have not placed anything from the right subarray. Okay. तो फिर हम चलते चले गए. What should I do now? Okay, I advance I, but now I again landed in a situation where J is pointing at 4 and I is pointing at 5. So clearly I need to now place 4 into the final array. And now I again increase count. By how much? Again it exposes some split inversions. Okay. But now it has exposed only one split inversion, which is 5. So it's only 1. Gaurav, it's not 0, right? We are at 4. So it's not, yeah, it's 1, exactly. Okay, so it has exposed another split inversion, which is 5, 4. And clearly that's a valid inversion. Okay, so now my count becomes 2 plus 1, which is equal to 3. Okay, remember, 2 पहले था और अभी 1 मिल गया और, right? So then I just keep doing this, and let me now finish this one, because clearly there is not going to be any more split inversion. So the merge procedure just ends. Okay. So any questions so far? So all we are saying is that this merge procedure that we have learned as part of our merge sort algorithm, that also exposes split inversions, given that you have the two subarrays X and Y in sorted order. This is very important. Yeah, otherwise we could not have made this claim. Okay, but this is just an example. But remember, we are trying to design an algorithm. Okay, so I think I have finished this. We are trying to design a general algorithm. So in general, what could be the claim that I want to make? All the split inversions are not exposed. So Siddharth, why do you say that all the split inversions are not exposed? So, okay, so here is what I will do. Let me go through 5, 2. 5, 2 was exposed when I counted 2 here, Siddharth. So 5, 2 was exposed when I dropped 2 into this subarray, right? So this happened actually quite early. So remember, in this slide, I had dropped 2 into the final subarray, and then no, both of them were exposed because I added a count of 2 here. I did not add a count of 1. Okay. So here, when I dropped 2 into the final subarray, I added 2 to my count. Why? Because it exposed both the split inversions. It exposed 3, 2 and 5, 2, both of them. Okay, it's very important, right? I'm not saying that I am only counting the inversion between I and J. Yeah, I'm counting all the inversions that are happening here between 2 and all the remaining elements in the first subarray, right? And this is exactly the general claim that I'm trying to make now. Okay, so let me show this pictorially once, just to make sure that we are clear on this. So I have X here, I have Y here. Okay, now suppose that in the merge procedure, I am currently at Y. Okay, I'm currently at this element Y, right? And so my the J pointer is pointing at the element Y of the second subarray. And here I have some element, I don't know, but let's say I is the pointer here. Okay. Now, suppose that in one iteration of the merge procedure, Y is going to be dumped in the final subarray. Okay. Now, what I claim is that the total number of split inversions that Y is involved in. Please note the statement very carefully. What I'm claiming here is the total number of split inversions that Y can be involved in is precisely the total number of elements that are remaining in the first subarray. What do I mean remaining? Those which have not been copied into the final array yet. So that number is roughly n half minus I plus 1. Okay, so I always confuse between this plus, a plus 1 rahega ki nahi rahega, but I think you understand what I'm trying to say. So the pointer I is at a certain point in the first subarray. All I'm saying is at this point, jitna bhi bacha hai till the end of this subarray, I actually Y is involved in a split inversion with all these elements. Okay. So let's just, although this is not very, this is not super hard or anything to imagine, Let's just write a couple of lines of proof, okay, just to convince ourselves that this is indeed the case. Okay, so the point is that if okay, for all elements x1 to xi minus 1, what is the relationship between small y and these elements, the elements between x1 and xi minus 1? Can y be involved in any split inversion with any of them? Okay, no. Why not? Exactly, because y is bigger than all of them. And why is y bigger than all of them? Because अगर bigger नहीं होता तो y अभी तक यहाँ पे नहीं रहता. Then y should have been part of the final array by now. But remember, y is still still not part of the final output array in the merge procedure. Okay, so it will be placed after those elements in the final array, which means clearly that y cannot be involved in a split inversion with those guys, with the guys xi to x minus 1. So they cannot count for any split inversion which involves y. Okay, so let me just write y is greater than x k. Okay, so for k equals to 1 to I minus 1. Similarly, for all elements xi to x n half, y is actually smaller than xk. Yes? And why is this the case? Well, I know that merge is going to place y in the output array, which means that y is smaller than the current xi. But since x is sorted, I know that all the elements after xi is even bigger than xi, which means that all of them are in turn bigger than y. And so y is involved in a split inversion with all of them. Okay, so I don't know who this is, but yeah, so remember I made this simplifying assumption that I have distinct elements, but if it's equal, then that does not. Yeah, you have to keep an additional check. So that doesn't count for an inversion. So that would just change your pseudocode a little bit. That's a very good point. Yes. So in general, an array can have equal elements, but that doesn't count for an inversion. That's the algorithm. Okay, that is it. So any questions about this claim? Right, Gaurav. Yes, we can subtract later. Yeah, you can do it in many ways. Okay. So I guess yeah. So this is just to show how to modify the merge procedure. So instead of merge, I now call this count and merge, and it's everything that merge is doing. The only difference is when we are in the second case of merge, that we are actually placing so basically what is the case? Yeah, so yj is less than x of I, then not only do I place the current yj into the output array and advance j, but I also increase the count of split inversions. Okay, by how much? By n half minus I plus 1. Remember, it's the number of remaining elements in the first half of the subarray, in the first subarray. Okay, that is it. So by the way, I think okay, Piyush, so D is the final output array. So जहाँ पे आप दोनों को merge करके आप output करोगे, right? So remember, in merge sort, you need a third array. So in merge sort क्या होता है? So when you are doing the merge operation, you have two sorted sub arrays, and then you have a third array which is storing the merged array of these two things. So D is the output array basically. Yeah. Okay, that's a good question. Which array are we calling recursively, D or original array? So, okay, so for that, let's actually look at the entire recursive procedure. So, okay, I think Siddharth was the one who asked. So remember, this is just your count and merge subroutine. This is not this does not have any recursion. So count and merge ka input kya hai? Count and merge ka input hai two arrays X and Y, which are sorted already. and each of which has length n half. So these you are already getting from your lower level recursions. Okay? So you are at a certain level and you are calling the recursive calls, and finally you are calling count and merge from that level itself. So you are already getting the sorted subarrays from x and y, sorted subarrays from the recursive calls in the form of x and y. And all you now need to do is combine these two. But remember, in a similar way that you are asking for sorted subarrays from your children, you should also have the responsibility of sending a sorted array to your parent. So which is why we are involving the merge procedure. And in addition, we are also counting the split inversions. So this is why I said that you should ask more from the recursive calls, and you should do more yourself as well. So instead of only counting, you should also sort the arrays. So yeah, this subroutine for free is also sorting your array. Yeah, it's essentially sorting and counting inversion, if you want to call it that. Yeah, I call it that actually. So sort and count inversion. Okay, so this is your entire routine, right? So if, yeah, so n equals to 1 is the base case, then you just split your array into two halves which are equal to each other, and then you call these two recursively. And remember now that this B and C array that we are going to get back from the recursive calls, they will be sorted versions of X and Y. Okay, but this is wrong. This should be B and C. Any questions? Yeah. Everything clear? Yeah. So the runtime is going to be almost the same as if there is index from 0, then no, Ananya, I don't think so. Why? Because this counts the number of elements, right? So this n half minus I plus 1, this is a count of the number of elements. This is not really has to do anything with the index. So no matter which I you are at, right. Oh, right. Okay, so Shruti asks an interesting question. Why are we returning x plus y plus z and not just z? Right, Shruti? So remember, so what is this routine? So what is this routine supposed to return? So you have an entire, so what are you supplying it with? You are supplying it with an entire array. And you are supposed to return all the inversions that are happening in this array from this subroutine. Okay, so you are, so the Z thing only counts your split inversions, but remember you also have to count the left inversions and the right inversions. So these first two things are actually doing that. They are counting your left inversion and right inversion, and then you are doing the split inversions. Okay, so that you are sending to your parent. Okay. Okay, you did not understand how the count and merge gets the sorted array. That's a very good question. Okay, so let's look at this subroutine. Okay, so when you are calling so let's say you have called one of its child, right? So let's say you have called this subroutine. Okay, तो इसके अंदर क्या होगा? It will again call the recursions on its own children, but remember at the end it will do its own count and merge subroutine. So whatever we are getting back from the children, that is going to be a sorted version of x. It's not going to be only like x is we are getting back x. We are going to get a sorted version of x, and this is exactly what happens in merge procedure, right? So remember, when we are implementing this, we are essentially implementing the merge procedure. The only additional thing we are doing is we are also keeping track of the count of split inversions, right? Yeah. Okay, good. Okay, so any further question? B is sorted X, absolutely. B is sorted X and C is sorted Y. Yeah, yeah, okay. So let me just look at the chat. So essentially, okay, so Keshav says, so essentially we are converting left and right inversion into split inversion. And then after sorting, we are returning the split in. Okay, okay, this is a bit hard for me to parse. Then after sorting, we are returning the split inversion, which becomes left inversion and right inversion at a level above. That is absolutely correct. Yes. So essentially you are, because through this recursion, you are essentially converting everything into split inversions. But remember, these are split inversions at different levels. A split inversion at level I might not be a split inversion at level I plus 2. So split inversions are not an absolute global quantity in your given array. They are completely dependent on what subproblem you are looking at. So this is exactly, yeah. Okay, it should be n minus n half in the second call. What do you mean? Gaurav, I didn't get that. Which one? You mean in the call in this one, the c comma y thing? So Gaurav says it should be n minus n half. Yeah, okay, I see. Yeah. It should be n minus ceiling of, yeah, okay. Yeah, I understand. Okay. Right. If yeah, for general n, that should be okay. But let me correct it later. Okay. Or not correct. Actually, I assume that it's odd, but I agree. I should be more precise. But let me just do this offline. Okay. Otherwise, I might make mistakes. Okay. So everyone understands what was going on here. Okay. Any questions? So this is how you implement inversion counting in linear time. Not linear time. Sorry, order n log n. Okay, sorted array is D, but we are not using it anywhere. So, okay, so Kshitij, when you are returning D, so basically, ye jo B hai na, this B is your D actually. So D is just in the implementation, but that is exactly your sorted array. So you are supplying this empty array B to your subroutine for this level, and after merging, you are getting it back. So that's what you are. Yeah, exactly. Okay, Rajkumar says, but array updates automatically. So why use BC in place of XY? No. That you need, right? You always need, for merging, you need a third array, Raj. So I think just revise your merge sort a little bit. You need a third array in order to do the merge. You cannot do this in place. That's why you need a third thing. It's not, yeah. Right. Yeah, n half plus 1 should be correct, I think. Yeah. Yeah, I'm just applying the number of elements to the two recursive calls. So, okay. Just give me a second. Okay. Okay. So, any more questions? Great. Oh, that's correct. That's correct. Yeah. You are right. Samarth, you are right. We also need to return D. Okay. Yeah. But I was assuming that, kind of D is like it's a container, right? You are supplying the container, and your recursive call is just dumping everything in the container. But yeah, probably you are right. Okay, so I guess so since we are done and I have like about 20 to 25 minutes, let me actually talk about a second divide and conquer algorithm. So before actually going into this, let me give you some disclaimer. Okay, so this is a magical algorithm. Like I don't. So the disclaimer is that I don't know why this person, whoever discovered this algorithm, came up with this algorithm. I think nobody does. But on the other hand, I am not going to go through every little detail of this, of some of the things that I'm going to say. Yeah, many of the things will appear intuitively clear, but some of the things, you know, you might have to do a bit of calculation and figure out that whether this is correct or not. So I'm going to give you those hints along the way, and I would expect you to just do these checks once you go back. Okay, right. All right. So matrix multiplication. Okay. So what is matrix multiplication? So suppose, so I hope everyone here is aware of what a matrix is, right? So a matrix is nothing but a bunch of numbers arranged into some rows and some columns. And the numbers come from a certain field and all that if you want to be really mathematical. But for now, again, you know, for simplicity, assume that they are all integers or something like that. And I'm assuming, so one is not an assumption. The algorithm that I'm going to describe here is used to multiply square matrices. Okay, so I will assume that I have two square matrices, both are n cross n. So X is a square matrix which is n cross n, and Y is a square matrix which is n cross n. And all I need to do is to find the product of these two matrices. Okay, right? Okay, so I guess we all know that so when we are multiplying two n cross n matrices, then what we get back is also an n cross n matrix. Okay, so Z should be, so the output matrix is also going to be an n cross n matrix. Okay. Okay, now, okay, so how do we actually multiply two matrices? So suppose, so all I need to do is figure out the individual entries of the final matrix Z. Okay, so suppose now I am trying to figure out the I comma jth entry of the final matrix Z. So the final matrix is Zij. So how will I find the product? Well, it's essentially what we call the dot product. So let me actually say dot here. So it's a dot product of the ith row of X and the jth column of Y. Okay. So suppose this is the ith row of J. So it's like one row, right? So this is row I, and I have the row J. Sorry, I have the column J. Okay. And if I want to figure out the Zi comma j entry, all I need to do is find the dot product of these two vectors, because each row and each column is like a vector. So I just need to find the dot product of these two. Okay. So that is like a vectory way of saying it. What I'm really trying to say is Zij will be equal to what? If I want to write the summation, let's see who remembers matrix products. So how should I write this? Okay, so this is going to be summation over all, right. So this is going to be summation over all the k's, right, from 1 to n, x I k times y k comma j. Okay, so that's the entry. That's the Zi comma jth entry. Okay. Good. So, okay, let's stick to this slide. Okay, so now let me ask you this question. So first of all, suppose you set out to design an efficient algorithm for matrix multiplication, okay? And you have an n cross n, you have two n cross n matrix, and your output matrix is also n cross n. What should be the aim? I mean, what is the best runtime that you can hope for? What is the best, I'm asking? I'm not asking you to. Okay, good. So it cannot be, again, it cannot be better than n square. Why cannot it be better than n square? Okay, so some people are saying n cube. No, I'm not asking of any specific algorithm. Okay, I'm saying that what is the best that you can hope for? So I claim that no matter how smart you are, you cannot design an algorithm which works better than n square, because clearly my storage, not only storage, okay, let's think about storage later, but again, even outputting or accessing the entries require n square amount of time. Yeah. So or even outputting the Z matrix, that will take up n squared time, right? Even if I forget about space and everything else. So clearly I cannot shoot for an algorithm that is better than n square. तो ऐसा हम नहीं कर सकते कि n log n algorithm हो जाएगा या n to the power 1.5 हो जाएगा, नहीं होगा. N square ही, you know, it's the goal that we are all shooting for. Okay, now the next question is, what is a naive iterative algorithm, or rather, what is the runtime of a naive iterative algorithm to solve this problem? How will you solve this problem? If you are seeing this problem for the first time and you are asked to write a code, what will you do? Well, then it's n cubed. Why is it n cubed? Well, this relationship clearly tells us an n cubed algorithm. What I will do is I will go over all the possible I comma j entries. Yeah, remember I have to fill up each entry of the Z matrix. So there are n square many such entries. And for each entry, I essentially need a linear time algorithm. Yeah. Why? Because remember, my I and j is now fixed for a fixed entry. All I need to do is I need to go over all the possible k's and just multiply the two corresponding entries. Okay. So this gives me what I call a theta n cube algorithm. Okay. So not only is it order n cube, it's also theta n cube. It will actually need n cube amount of time. Yeah. And it will not take more than n cube amount of time, barring the constants and all that. Okay. But so again, the obvious question is, can we do better? Can we actually get an n square algorithm? Okay, so Gaurav asks, how do you know it's theta n cube? Well, because you need to do all these things, right? I mean, you cannot just get past computing any of these given quantities. So you need to have n cube many operations, Gaurav. So when we say order n cube, it's like at most n cube. But I'm saying here that you actually need n cube operations. You cannot do with less than that. You need n cube many multiplications, right? All right. Okay. So, okay. So what is the best runtime I can hope for? This is order n square, and naive algorithm takes theta of n cube. All right. So can we do better is the question. So since we are studying divide and conquer, of course, now we would like to apply divide and conquer. Okay. Now, again, so what is the setup? So I have been given two matrices. Now, the first idea of divide and conquer could be that, okay, you just take you just take a matrix which, let's say, only takes n half columns of the X matrix and all the rows of the matrix. Okay, what is the problem with this idea? So suppose I just divide my matrix into two halves. I just draw a line in the middle and I try to recurse over the left half and the right half. Very good. Okay. So if I do that, then the smaller subproblem is no longer a square matrix. Remember, here we are only multiplying two square matrices. And when I'm talking about a recursive algorithm or a divide and conquer style algorithm, then my subproblems should have the same nature. Yeah, I cannot just use a different problem as my subproblems. Yeah, so that's not a good idea. So the next obvious idea is to divide your matrix into what I call quadrants. Okay, so what are the quadrants? Basically, yeah, it's what this picture is showing. So you think of your square matrix and think of dividing it up into 4 quadrants. So each quadrant is essentially n half times n half. Okay, why we can't divide? So Nikhil asks why we can't divide it into only half. So Nikhil, the problem is, suppose you do that, then what is going to be your smaller subproblem? Your smaller subproblem is going to be this rectangular shaped matrix. Yeah, but this rectangular shaped matrix is not a square matrix anymore. Remember, but we are only interested in multiplying square matrices. So the recursive call that you are going to do, whatever that is, that will involve rectangular matrices, and that is something we want to avoid. We don't want to go there. We still want to be able to call the recursive subroutines on square matrices. That's why we are dividing up into quadrants. Okay. All right, good. So now, again, as I said, that there are certain things that I'm going to hide under the rug and leave it up to you to check. So what I claim is that if I'm able to write my matrices in this fashion, then I can write the products. Then I can write the product of these two matrices also in the intuitive fashion. And what is the intuitive fashion? Well, it's essentially like multiplying the matrix. So imagine this A, B, C, and D to be individual elements of a 2 by 2 matrix, and then the product matrix will exactly have those elements as each of its elements. Okay, so it's as if I am multiplying two 2 cross 2 matrices. So the first, like this northwest corner is going to be exactly AE plus BG. The next one is going to be AF plus BH. This is going to be what? CE plus DG. And the last one is going to be CF plus DH. Okay, this you check. So I'm not going to prove it because this is all dirty algebra and nothing else. But I think it's a good exercise for you to check that this is indeed true. So all I'm saying is, if I'm able to write these matrices in the form of these block matrices of n half, then the product can also be expressed in terms of these blocks. Okay. And now we are in game. So why are we in game? No, Harsh, it's not at all clear whether we are n square log n or not. We have to see. Abhi bahut dur hai. Okay. Good. But now at least we are in game. So why do I say that? Why are we in game? So what should be the divide and conquer algorithm now? If I tell you this information, if I give you this information, then what is the divide and conquer algorithm that you will actually apply here? Well, it's basically the same thing that we did for multiplication, right? For long multiplication. So what is going to be the first? So what is going to be the first step, right? So you recursively. So step 1. Recursively compute the 8 products. Okay. And then step 2 is do the additions. Okay. So that's my divide and conquer algorithm. Okay. So now there are 2 things that I need to check. Of course, we have to first figure out what the runtime of this algorithm is. That is not yet clear. But let's first check. Okay. So what is going to be the runtime? So again, we need to write a recurrence here. So each level of subproblem is actually computing 8 products. So I am invoking 8 many recursive calls. So what is going to be my recurrence? So then the runtime, what is going to be the runtime? Tn equals to what? Okay, it's 8 t_2, right? Why is this 8 t_2? Because remember, I am finding 8 different products, and each of these products each of these products are n cross n over 2 cross n over 2 matrix products. Okay, so I'm exactly calling myself 8 different times. But then I have to do a bunch of additions. So how much does each addition take? How much is each addition taking, roughly? So it's roughly order n square, right? Let's just keep in order. Let's just forget about constants. Yeah. So each of these additions is going to take order n squared time. Why? Because each of the products that has roughly n square many elements. And then when you are adding those two, you are just adding entry by entry. So the corresponding entries you are adding up. So that will take order n square. And there are like 4 of these that you need to compute. So it's roughly going to be 4 times whatever the addition time is. So overall, I can just write order n square, okay, or c times n square. So what is Tn then? How do I compute Tn now? So if this is my recurrence, okay, master theorem. So who can apply master theorem and tell me what the answer is? Good. So it's going to be n cube. Okay. Why is this going to be n cube? Which case of master theorem are we in? Well, here, so master theorem with a equals to 8, b equals to 2, and d equals to 2. Okay. So this is going to be Tn equals to order of n to the power of log 8 base 2, right? Which is going to be n cube. Sorry, this is bad. So this is going to be order n cube. That did no good, right? तो इतना मेहनत करके या इतना क्लेवरनेस लगा के क्या हुआ, फिर से ऑर्डर n cube हो गया, right? But we should not lose heart. Why? Because the same thing happened when we were trying to multiply two numbers. We saw that the naive recursive algorithm actually gave us an improvement. And especially, where did the improvement come from? Where the improvement came from? Because instead of computing 4 different products, we saw that computing 3 different products is enough. Okay. Now, in this case, this is not at all obvious, but that's where Strassen came in. So in 1969, he actually gave an algorithm which is again recursive, but now he could do away with only computing 7 cleverly chosen products. Okay. So how he cleverly chose these products, we don't know, but I'm going to show you what those products are and why they work. Like why they work in the sense that I'm going to write the math. But honestly, I have no idea how he came up with these products, okay, and why he did that. Okay. And then again, you perform a bunch of constantly many additions and subtractions over matrices, okay, which will take order n square. So what is going to be the runtime now? If instead of 8 recursive calls, I do 7 recursive calls, then what is going to be Tn? Well, now Tn is equal to 7 times Tn half plus order n square. Okay. So again, if you apply master theorem, so applying master theorem. So yeah, I'm just going to give you the number. This is going to be n to the power of 2.8704. Okay. Now, for those of you who are wondering that, okay, I mean, how better is n to the 2.8704 compared to n cube? Actually, I have used a plot in order to convince you that it is actually quite different. Okay, so that's the plot between x cube and x to the power of 2.8074. And as you can see, already at n equals to around 2000, these are quite divergent. So you can imagine how largely they will diverge. as you go towards higher and higher values of n. And indeed, because of this thing, because of this advent of machine learning and data science, multiplying large matrices is extremely important these days. So this is indeed very useful. Okay, so Soham asks, no, I did not get log 7. Soham, this is just plugging master theorem with a equals to 7, b equals to 2, and d equals to 2. Right. What were those 7 products? That will be the next slide. Okay. Because this is very mechanical for me, so I want to defer it till the last point. Okay, so no more suspense. Let me actually write the 7 products, okay? And you have to bear with me a little bit. It will take some time to write the product. Okay, so again, remember what was X? So X was A, B, C, D, and Y was E, F, G, H. Okay, so product 1 is going to be A times F minus H. Product 2 is going to be A plus B times H. Product 3 is going to be C plus D times E. Product 4 is D times G minus E. Okay. P5 is equal to A plus D times E plus H. Product 6 is B minus D times G plus H. And the final product is A minus C times E plus F. Okay, unbelievable. And yeah, no, I don't remember. So I have my cheat sheet. No, there is no question of remembering this. Okay. Are you mad or what? I will remember this thing. Okay, I will forget my name if I have to remember this. Right. Okay, so now what is the magic going on? So let me give you the final thing. So basically, remember what the real quantities that we're interested in are these things, right? So for example, this is AE plus BG, AF plus BH, CE. So Soham, just that's an interesting question. So just hold on to that thought. Okay. Yeah. CE plus DG, CF plus DH. Okay. So remember, eventually we are interested in these 4 quantities. So now what I'm going to show you how to express these in terms of the P's that we have computed. Okay. So this is actually P5 plus P4 minus P2 plus P6, P1 plus P2. This is P3 plus P4, and this is P1 plus P5 minus P3 minus P7. Okay. Yeah, so this is all information bombardment. As I said, I don't know how to do that, but okay, so first of all, I think the whole business is clear to everyone, right? What is going on and how he came up with the how this gives us the improvement. Okay, and please check these things once you go back, right? Why these are all true. Now there were a couple of interesting questions. So one thing is, if you notice, there is a kind of a similarity in the thought process of Karatsuba and Strassen, and indeed, Strassen was inspired by Karatsuba to. In order to sort of come up with this algorithm. But the point is that, so people have tried to imagine that now, is there any underlying principle going on when we are going to when we are always doing this thing, right? First, we are trying to find out the naive recursive calls that we need, and then we are somehow being able to express these products in terms of a fewer number of products. So is there any general principle going on when we are trying to do these things? So indeed, people have, okay, it's not completely understood among mathematicians, but indeed there has been some effort. So that involves a lot of group theory and set theory. And honestly, I am not qualified to even comment on them. But it turns out that people have started understanding what is the underlying principle that is going on, which in some sense might reveal the thought process of these people. Of course, this came out just as a stroke of genius. I mean, yeah, this is a person who constantly plays with matrices, and somehow these patterns just emerge. So the more and more you work with math, the more and more you work with numbers, somehow these patterns start emerging, and it's more like an art. It's very difficult to explain how we come up with this product, but hopefully someday, if these set theorists are able to or the group theorists are able to understand the underlying principle that is going on, then we might be able to make even faster progress. Okay, so now I think there were a few questions of how do we know that 7 is the right number? Why can't we do 6? In fact, the big open question is, can we get a quadratic algorithm to solve matrix multiplication? Okay, so let me end today's lecture with some trivia. So note that Strassen came up with the exponent 2.8074, and there has been, so I wrote 15 here. Actually, 15 research papers are the most important ones, but there are more papers written on this topic, just on the topic of multiplying two n cross n matrices. And people have applied techniques starting from, so I'm just throwing information again, starting from fast Fourier transformation, discrete Fourier transformation and whatnot. Okay, so it's so much interesting yet among algorithms that, as recently as this year, two people from MIT, Josh Allman and Virginia Williams. So Virginia is actually involved in many of these 15 papers over the last few years. So they came up, so the best they could come up with so far is 2.37 roughly. Okay. Now, there are two issues here. So not two issues. I mean, there are two open questions at this point. So first is, can we actually get down to a quadratic algorithm? Can we find a purely quadratic algorithm to multiply two matrices? It's not known. And we don't have any reason to believe that this is not possible. Maybe this is. But for me, a more interesting question is that Strassen's algorithm is actually the most practical among all these improvements that have been done. When I say that, what I mean is these algorithms only start showing their advantage when you are multiplying huge matrices. And huge means really, really astronomical. So these are matrices which we will never probably multiply in practice. Okay. So unless you go to that regime of n, these recent improvements really do not. So they are extremely deep theoretical papers, but they are not really practical algorithms. So Strassen is still the method of choice. And remember, someone doing this in someone did this in 1969. Okay, so that's quite brilliant. So that's what I wanted to say. Hopefully that motivates some of you to do research in this topic. So I will stop here today, and I can take some questions if you have any.